This particular talk. This is a joint project with one of my thesis students, and we are working on this project on microinsurance. So you have heard microfinance, micro, various other things, but very rarely you hear people talk about microinsurance. So to start with, let me just give you a brief background of what is the difference between a microinsurance and just a regular garden variety insurance. Microinsurance in this context, what we do is typically we sell a product which is very simple in structure. So if you think about life insurance, and if you want to buy life insurance policy, you can buy a life insurance policy of any face value you care to name. So if you want to say, I want to buy a life insurance policy which is worth 12,432 rupees and 45 paise, you can do that. Most people don't do that, but the policies are like that. So you can basically scale the thing up whichever way you want. So that's how the policies are written normally. Microinsurance policy, on the other hand, does not do something like that. What it does is gives you a short menu of things where the face values are very round, big numbers, and the price or the premium is also correspondingly relatively easy to understand. So the whole idea of microinsurance is to sell the product to people who are not very familiar with this kind of thing, who are probably not very literate, and so on and so forth. So the whole idea is to simplify the structure of the product to sell it to a particular audience. And a lot of these microinsurance products are also typically subsidized by the corresponding governments. So for example, in India they sell microinsurance for life insurance that come as a byproduct when you buy a bag of seed grains for your sowing, whatever you're sowing. As a result, microinsurance products are relatively simple products. Having said that, it serves a very important social function. So to start with, economists generally do not want to give subsidies to things where typically we know the subsidies do not go to the people to whom they're intended. For example, if you give subsidy for cars or gasoline or petrol, we know that when we give 1 rupee worth of petroleum subsidy in India, the bottom 10% of the people get less than 1 paise of it. Most of it is captured by the people with more money. Why is that? Well, more people with more money means they are likely to have cars, which means they are going to get this subsidy. And the same thing goes on with other kinds of things. So for example, oil subsidy, the LPG subsidy that we give in India, most of it is captured by the middle class in the cities. Why is that? For example, right now they have these complex rules where you pay the market price, but then the government give you back certain amount and deposit into your bank account. Well, who has a bank account? Mostly people in the cities. And who use the bank account? Mostly people in the cities. So as a result, these kinds of things tend to not help the people whom they are directed to. There are certain exceptions, and this product that we are going to talk about here applies much more. They are much more focused, as you will see in a second, for the right market. As I said earlier, that this is a joint project with one of my thesis students. Right now she's somewhere in the jungle in Cambodia, so I don't know what she's doing right now, so I'm doing the presentation. Okay, to give you a dimension of the problem, there are approximately 3 million people in Mexico out of about 120 million who live without electricity. So of course, by Indian standard, this is a very small number. But Mexico, which has a per capita GDP of about $12,000 a year, this is a very big deal. That 3 million people actually do not have any electricity whatsoever. And that accounts for about 600,000 households. What is more important for the Mexican context is that most of these people are also indigenous people. So there's a whole set of programs directed for these kinds of people who live on the margin. And so this particular project is one that has full support of the government. It has full support of the World Bank and the Inter-American Development Bank. So all of them are willing to finance a project in Mexico and similar projects in the rest of the world, in Africa, in other parts of Latin America, or in Asia, as long as they are sure that whatever the project is, the actual beneficiaries are largely the people to whom they are intended. So it does not happen the same kind of thing as I mentioned with the LPG and other kinds of stuff. In fact, we do know that, for example, in the case of petroleum subsidies, the petroleum subsidy given in the entire world is about $450 billion a year. And most of it is given by the developing countries' governments. And they spend much less money on things like green fuels and so on and so forth. So on the other hand, these countries are spending $450 billion a year subsidizing the greenhouse gas producing stuff. On the other hand, they are turning around and asking the developed countries' government to give them money. So most developed countries, of course, say, why would I give you $200 billion when you are spending on yourself $450 billion? So there's a lot of contradiction and conflict in this sort of area. I'm not going to talk about that, but that's another stuff. So as I mentioned, these people mostly live in rural areas, and what is most important is that the government currently has absolutely no plans to connect them to the electricity grid at all. Why is that? Because the costs are prohibitive. To connect two households which live 120 kilometers away from the nearest power supply or last post of the power supply makes no sense. The cost is too high. So what do we do? Well, one of the options is to move these people away from there, and if they voluntarily move somewhere else, they vote with their feet, they go somewhere else, and the problem is solved. Of course, that's not a realistic solution for various reasons, for cultural reasons, for economic reasons, and a whole host of other things. So given that these people are going to stay where they are staying, we need some alternative methods to connect them to the electricity, not through the grid, but through something else. So what kind of usefulness do they have for these households? Well, to start with, as I mentioned here, the poor households spend about 10 to 15% of their income on energy. So that's a substantial chunk of their income they spend on energy. What kind of things they use? They use things like kerosene, diesel, or candles. So we're talking about very, very basic stuff. What is the problem with that? They're typically very expensive. So if you have to use kerosene, you spend about 15% if you're at the lowest 10th percentile or 5th percentile of the income level. Then you're spending about 20% of your income just buying kerosene for burning lamps. And what's the problem with kerosene or any of the other stuff? They are very toxic. So these people, imagine these people live in small huts, and when you burn kerosene inside the hut, it pollutes the air inside. There is no other possibility. You cannot open the sides, because if you open the windows, well, the lights go up, lights go out, or it produces these toxic substances. And typically they are of low quality, meaning that you get light, but they are very low intensity. So they are not as well as their alternatives. As a consequence of that, you get two outcomes, and these are very well documented outcomes. One is you get little children with a lot of respiratory problems. So they have more coughs and colds, they suffer from more bronchitis, and we know all of them are related to this fuel burning inside the house. And they also are more prone to getting burns and stuff. So if you have a kerosene lamp, 2-year-old comes and pulls something, falls on his head, gets burned. And that's very common on Earth. So the people who are affected by all of this are mostly children. And so basically what we are doing is we are reducing the human capital value of these people over their lifetime. The option that they are considering is solar powered things. So what kind of things? For example, solar water pumps. And they are typically, if you have hand pumps, they are much more labor intensive to operate, and so on and so forth. Solar water pumps are much better. And then you have this possibility of refrigeration. So you might say, well, you don't need to eat ice cream if you're poor. Okay, but that's not what we're talking about. We're talking about things like rural health clinics, which does not have electricity. So they cannot store anything, injections and things like that, which require refrigeration. And a lot of these kinds of medicines do require at least minimal amount of refrigeration, and that cannot be had if you do not have electricity. Then you have these community centers where they actually teach these rural people how to farm, how to do this, how to do that. Small things for people who live in the cities, but very big deal in a village setting. And lastly but not the least, rural public lighting. Again, if you have sparsely populated area, it makes no sense to bring in the electricity grid where you are burning electricity for somebody passing by 1 in 2 hours. So what these solar lamps can do is to illuminate, when somebody is passing, it has a sensor, light comes on and then it turns off after a while. So this is what it actually looks like. So here's a lady who's holding her solar powered solar panel that they actually are going to use in their households. And this is what it looks like on the inside. So as you can see, there's a lot of light that comes out just one of these solar powered light bulbs. And as you can see, she also has a mosquito net, which is also another problem, not related, but having a mosquito net makes a big difference in terms of, especially for children who can contract malaria and things like that. That can be very useful. And the third thing, you notice that she's doing something. Actually, she's working to make certain kinds of Mexican chutney for cooking and stuff. And they would actually sell that in the market too. So if you can work during the night, otherwise these kinds of businesses are not possible. So having longer periods in the night to do some economic activity actually helps them to have a better life. So it has a lot of other side benefits or externalities, as the economists call them, that also have to be taken into account. So it's not just just giving a light to one person. And as I mentioned, they can be used for water pumps and things like that. Here's one example. You actually don't need a very large solar panel to generate water pumps and things like that. These days they're relatively small. And these solar panels can help them to use it for that purpose. As I mentioned earlier, that in the rural area, generally the problem is these people have very little formal education, and what impact that has we'll see in a second. On the average, these households have 4.6 years of formal education, so not even 5th class. The illiteracy rate is 27%, but actually that's an underestimate, because most of the times in these places, to find out if somebody is literate or not, basically the census guys go and then they ask, can you sign your name? And a lot of these people just sign their, they learn by memory those letters. So they don't mean anything to them, they're just like little pictures. So they learn how to sign their name, but that's all they can do. They cannot read and other stuff. So the illiteracy rate, that's the lower bound of the illiteracy rate. The actual illiteracy rate is closer to 50% among these people. So what does that imply? That implies that you need an apparatus which does not require reading instructions. So you know how if you buy any electronic product, you know how it is. They come with this long-winded explanation about how to use it, written somebody in Taiwan. Even though it's in English, you cannot decipher what it says. And so it's always a big problem, right? So what you need to have for these kinds of product is something that somebody can read really, really easily. So what they do is they put the kit, it comes in a kit. The kit is actually color-coded, so if something goes wrong, people with relatively little education can actually put it together. And they're color-coded and intuitive. I have a picture of this. So, basically you can't see on the back, but it has the bit in black goes into a hole which is surrounded by black. So you just tell them the black thing goes into black and the red thing goes into red. That's all you need. And the rest of the stuff doesn't matter. So this is the controller which you can actually attach several apparatus onto the same solar power unit. And so it has a panel which obviously has to sit in the sun. And in large parts of Mexico, you get a lot of sun. You get 300 days of sun. So that's not a problem. On the other hand, if you want to install that, say in England or something, it's not going to work as well. Okay. So the impact of the apparatus that we have leads to better education of children. Why? They can read at night. It's not a problem. And they suffer less from asthma and other problems. So that also helps. Reduces the risk of fire and burn, as I mentioned earlier. Less smoke inside the hut, which means less respiratory diseases. And as I also mentioned earlier, it leads to more hours of work inside the household at night. So as a result, you increase the productivity of these people, and as a result, they will have higher income. So that's the whole background of this stuff. There are two problems that we need to face. Number one, the cost of the apparatus. There are two models that you can buy things off the shelf and put it together at a relatively low price. Even though it's a relatively low price by international standards, it still costs $240. The smaller unit right now, the bigger model costs around $300. So it's not an insignificant sum for these individuals or these households to invest in an apparatus like this. The second problem that arises comes from the maintenance problem. Why is that? If it breaks down, remember these are remote households, so you cannot just go to the nearest store and buy all the replacement parts and immediately replace it. It's not easily accessible from your place. So what you have to have when you sell this stuff, you have to have first a way of financing this stuff. So presumably the idea is generally that if you can finance it, these people will have higher productivity and therefore they can slowly pay it off over time. The maintenance cost, you need to have a mechanism by which somebody goes around periodically to all these places and checks all these things. If you have something broken, that person will have the spare parts and replace the stuff. And the third problem that we are going to address, we are addressing is that of lack of insurance for these products. So this is the part that I'm going to talk a little bit more about. To insure something, you need to know what are these components that actually constitute the whole apparatus. In the traditional model of insurance of this kind, what has happened is that the insurance products in other countries where they sell this stuff, they typically say, okay, we have two states of the world where the apparatus is working or not working, and that's all. And they will calculate simply the probability of not working, and from there do the calculation. What we want to do, what we are doing, is to actually split them up into different components. I mean, it's not rocket science, but we split them up in different components so that we can have a better handle on the probability of loss. And that way, we can better price these insurance products. Otherwise, they are typically overpriced. And if they're overpriced, then their demand falls accordingly, and therefore, not many people buy them. It's kind of like if you buy a 100,000 rupee computer and they say, okay, we have a plan by which we can maintain your computer next 5 years if you sign on the dotted line. So you read the thing and it says we charge you 20,000 rupees a year. Then you say, this is not worth it, I'm not going to buy this stuff. The same sort of thing happens here. So what we did was we identified each of these components as such. First there's battery, and then we went on to list what kinds of problems do these batteries have. And that's where the engineers come in, who actually know something about the probability of breaking down of each of these components and each of these sub-problems for each component. So for example, the battery. What is the biggest problem? The battery's biggest problem is discharges and all the liquid goes out, which means you cannot use it anymore unless you put in the liquid and repair the discharge. And there are leakages which are similar sort of thing. And then you have got problems of inverted polarity of the thing. And then a lot of these remote places are places where the temperatures are extreme. It goes from minus 10 degrees Celsius to 40 degrees in the summertime. So there's a lot of temperature variation, which means that the apparatus, the battery expands and contracts, which makes it brittle and it breaks down. There are terminals that are ruptured, that are connected to this whole thing. Then you have the solar panel itself, which sits typically at the roof or some high place. You typically have the problems that it's generating electricity, but it's of very low voltage, which means you cannot run the pump. If the light comes on, it's very low powered light, and so on. So that's a very common problem. You have shorted cable that comes down from the panel to the controller. The controller itself typically have two large problems. One is you generate false contacts, or they get burned out easy. The light bulbs that, assuming it's a light bulb, it's a pump, it will be similar. In the case of light bulb, you typically get the problem that it blinks. It does not give a continuous, produce continuous light. Does not light at all. That's the second largest problem. It gets cracked. These are very delicate instruments, and if you rough handle it or something happens, somebody throws a stone, it breaks. and that sort of thing. So what we did was to, we've got actually several thousand of these apparatus installed in a set of households, and we went around checking. I mean, we doesn't mean me or my thesis student, but other people who are actually in this business. They go around measuring these probabilities of losses. So here's the insurance problem that we are doing. How much should you charge for insuring these products? So that's our basic question. To answer that question, we need to have data on breakdown of each component, and each component does not have the same expected life. That's the other problem that we have to take into account. And that replacement can take time. When, you know, if your panel breaks down and you have to have it replaced and it takes 6 months for it to get replaced, well, you do not have life during that time. So your productivity goes down. To solve the second problem, as I mentioned earlier, we have periodic village visits. So some guy goes around in his motorcycle, goes around the country, well, there are several of them, and actually checks periodically in each village. So they have a schedule where they say, okay, we are going to come back to this village every 15 days or something like that. And so, you know, at most you have to wait these for 15 days. Sounds like a lot of time, but if you're living in a remote village, you are not pressed for time. Typically. So what we did was to actually price this stuff, what is called insurance pricing. So I thought I'd spend some time on talking a little bit more about how does insurance pricing actually work. So basically what happens is the following. You typically have 4 components. One is what are called expected loss. So if you think about a distribution, expected loss typically refers to just the mean value, that's all. So when an insurance person talks about expected loss, that's what they're talking about, mean of the distribution. The second part they will talk about, typically an insurance person, would be a non-expected loss. So non-expected loss, in English may mean lots of different things, but for insurance people, it means something about the variability of that random variable. And typically when we say variability, it simply means some multiple of sigma. So obviously that means you have assumed that the distribution has expected value, it has variance. Well, actually we just going to need those 2 parameters and nothing else. And suppose we know the distribution of losses, we can fix probability of loss in a given year, and from that we can calculate the non-expected loss. So basically, in operational terms, what that means is you calculate the mean value, say mu, plus some multiple of sigma. That multiple will depend on the risk tolerance of the insurance company. So let's talk a little bit more about how exactly do you calculate that constant. So let me just give you a very simple example. Suppose you have independent and identically distributed losses for a large number of these items. Then you simply apply law of large numbers and then say, okay, so everything is normally distributed, and therefore you can apply law of large numbers to calculate the loss for your portfolio. Remember, this portfolio that you're constructing is really the sum of all these individual losses. The aggregate loss is actually increasing with your size of the portfolio, but it's increasing at a slower rate. If your portfolio is size is n, the loss is increasing at the rate of square root of n. So that's how, in that sense, you say the loss is not going up at that rate. A lot of people make the mistake of saying that portfolio, look at the average value of that, but you are not insuring the average portfolio. Your portfolio is the sum of all this stuff. So it's not actually decreasing, but increasing at a slower rate. So as I mentioned, you apply law of large numbers because you somehow believe that these losses are IID. So what about the risk tolerance? Well, that depends on the insurance company. So suppose the insurance company says, I'm willing to accept losses once in 100 years, which means the probability of loss that they are willing to accept is 1% or 1 percentile, top one end of the distribution. So if it is normal, we know a pretty normal table, 2.34, and that's that. So then an insurance policy, any kind of insurance policy, incidentally this does not apply just to these products, but any insurance policy, when they price them, this is how they do it. So there's a concept called the pure premium. The pure premium is what? It's simply the mu plus that constant times sigma. That's it. So that's what insurance people call the pure premium of the policy. So do you charge pure premium? The answer is no. There are two other elements that an insurance company has to take into account. First of all, it has to make money. They are not in this business for charity. So they will make certain amount of profits. The other thing is, to sell insurance products, you have to have the infrastructure of the company, and it costs you something to sell the product. And so all of these things have to be taken into account. And how much are these costs like? Well, it's kind of hard to calculate depending on the product. It varies a lot. For these kinds of products, for simple insurance products like microinsurance, they are in the order of magnitude of 5 to 10% of the expected loss. It actually technically depends on the non-expected loss too, but for these kinds of products, we can ignore that. Okay, so summarizing what the pricing involves is you look at the expected loss plus the non-expected loss plus the profits plus the cost of selling. How much should the profits be? Well, typically if this is a financial product, an insurance company can get into this business or other kinds of business. So you look at the, say, average profitability of that industry and you say, okay, I'm going to take my average profitability as my target profit. Of course, that doesn't mean every year the company makes that profit. Some year they make losses, some year they get more money. But on the average over the long haul, they get, let's say, 10%. So that has to be added. So typically, if you look at how insurance pricing is done in the market, they just do these 4 elements. The other, if you think about this in terms of the market, what we are doing here is looking at the supply side of the market. Yeah.
In insurance pricing, we look at 2 things. One is the frequency and the severity. So this addresses the severity part.
And the frequency as well.
Severity of loss.
Yeah.
So how is the frequency of loss component getting priced?
Well, let's think about a lottery where you have the probability of loss, and with certain probability nothing happens. So this is my lottery, right? So suppose the loss is C, and here I don't lose anything. So think of at any year, either loss happens or loss doesn't happen. If loss happens, you lose a certain amount C. Okay? So think of this as one single unit. So basically, if you sell n of these things and you apply law of large numbers, then you say my mu is going to be n times C times P, and sigma is going to be square root of C square P times 1 minus C. That's it. That's it. So I have my loss of the portfolio for these identically distributed things would be a normal with this mu and And from that you calculate the pure premium.
See, when you are selling a large number of insurance policies, it is sold with the belief, and when you look at the empirical data, how many claims that get triggered over a given time.
So that's when you need two things: frequency and severity. So this is my frequency, you estimate some value, and this is my severity. You, based on your past performance, you calculate that stuff.
So very few policies have the insurance, that contingency events. It is upon the contingency of that event happening or not happening. So when you look at the numbers, this is a lot of policies will have zero triggers and very few policies. So it's a very heavy-tailed distribution.
Absolutely. So
I'm not
that's what, even if it's heavy tail policy, if you have N in the order of 10,000, it's fine. You can still apply law of large numbers. If the N is 20, then you cannot. Okay? So if you are selling 20 policies, and the probability of loss is 1 in 1,000, things are going to happen very, very infrequently. And when it happens, you will have a heavy loss. So then you cannot apply the law of large numbers. So what they would do is typically they'll say, okay, what are the small sample properties? And then they will go into doing something like that. But these are very small policies, and they sell in thousands. So we can apply the law of large numbers here. Not for all insurance policy you can apply the same thing. I do not want to give the false impression, but when you do some pricing, typically what you have to do, you have to submit it to the regulatory authority. So for example, in this case, in case of India, you have to get an authorization from the IRDA.
Yes.
And what the actuary has to do in the policy, they have to actually show this kind of stuff, and they have to do some simulation to show how much the losses are going to be over the next 50 years, over the next 100 years. And that's how you do the pricing.
So I have a PhD student who works on automobile pricing. So we use what is called as zero adjusted inverse costing.
Right.
Because all this gets lumped up on one side. So I find it very difficult to estimate parameters, because you have a lot of policies where the loss doesn't get triggered, and where it gets triggered, the severity is very high.
Yeah, the general automobile policy has another component which is not here, and that is a deductibility clause or a co-insurance clause. So suppose you have a 20,000 rupees deductible. Below that threshold, nobody is actually reporting, and that biases your sample, because there could be a whole host of people who are having 18,000 rupee losses. You think they are clean, they are not having accidents, but they actually are. So you have to adjust for that deductibility question, which a lot of the insurance policies do not. And that's a very important point for automobiles, perhaps not so, but health insurance problem, it's a very endemic problem. You think that in your portfolio you have a whole bunch of healthy people, but they may be going to the doctors very frequently, and they're just not telling you that they're going to the doctors because they don't have to. And also depends on the kind of questionnaire you generate. Because when you sell, you ask a whole bunch of questions, but if you are not asking the right question, then they may be not answering the things that you would really like to know. And it's also state verification problem, because you don't know certain kinds of things. So for example, if I ask, did any of your parents die of heart disease? Of course, if my parents died of heart disease, I'm going to say no, because you have no way of verifying whether they did or not, right? I do not have to submit birth certificates of my parents to buy life insurance policy for me. So people lie, and we do know that that's what happens. For other kinds of things, there's also a self-selection problem. The people whom you attract are also the bad risks. The good risks know themselves that they're low probability risks, so they stay away from it. Okay. So this is, as I mentioned, this is total price from the supply side of things. What this does not include is what happens on the demand side. Okay, I price the product, looks like a great product. What if nobody wants to buy? So that's where the insurance agents come into play for normal insurance. What they do is they will tell you as an actuary to an actuary that, okay, this is a good product, but this will have no demand unless you do something about the product. You could, try to price it in a different way. So for example, you might say, okay, if you continue the policy, we'll give you discounts and things like that. So basically, you do some kind of non-linear pricing, essentially. That does not solve the problem, but that minimizes that demand side problem. So here what we are looking at, to summarize, is all supply side things. So here are some numbers. So we calculated from the data over a period of time, what kind of problems do the batteries have. So these problems are specific ones that I mentioned earlier. One of them has a probability of 1 in 1,000, 1 in 7 in 1,000, etc., etc. So these are the numbers that we use, and then we add them up. So essentially, what do we get? We get the following. For the smaller models, when we do all these things with reasonable numbers, the insurance adds up to about 15% of the price, which is a reasonable number, so that we know that people would be willing to pay for that to buy this insurance. The bigger model, it adds up to about 18% of the price. At first I wasn't sure why the bigger model comes up with a higher insurance pricing. But it turns out that when you have bigger panels and things, they are more prone to more right-hand tail events. Something goes wrong, some lightning strikes or something, then the whole thing is completely zapped. And so the losses are bigger. As a result, the bigger model ends up with slightly different insurance costs. That's it. Are there any questions?
So what is the advantage of dividing it up into several?
See, if you do not add up the components separately, to start with, not all your components have the same life. So for example, the solar panel has a life of 20 years, whereas a battery has a life of 5 years. And so the replacement of the thing does not have the same cycle. And if you just lump them all together and say, okay, my losses are either P or C or 0, and that P represents all the possible things that can go wrong, you might be grossly overestimating or grossly underestimating these probabilities and the losses. So the advantage of having these component by component is to avoid that and not lump everything into one single thing.
But what if something goes wrong which is not adjusted in the components, so they don't get paid for that?
No, the list is actually pretty long. It has everything that can possibly go wrong. Yeah. With one exception, theft. It does not account for theft. But other than that, everything is priced in.
So the probability that you're estimating for different problems, those are just frequency, relative frequency from the table?
That's all. From the data that we have over a period of 3 years of about 9,000 observations, we do those calculations. Actually, one of the component is a lightning strike. I was surprised how frequent that is. I thought it would be a very, very low probability event, but it's not. Apparently, because you put the engineers told me that you put the thing up on the roof, so it's kind of like a lightning rod. It tracks the light.
You consider all these probabilities as independent? Like for example, your battery going out versus some
We do.
Or do you have some crossover?
We do, because we do not have a good handle of if there is dependency of any sort. We don't know. I mean, this we think as the first cut.
And this has no influence of demographic features or user-specific risks coming in. So this is all risk emanating from the product.
Correct.
Right. So let's say a man operates this equipment versus even a woman is going to operate this equipment.
Yeah.
Will that increase or decrease the risk?
The short answer is I don't know. We do not have the demographics.
In the insurance pricing literature, there is a huge influence of gender diversity. That is
Yeah. Of course. If you think about car things, the accident rates among women is much lower. But in this case, these are passive objects sit on the roof. So who does what should not matter, I would think. But actually, we do have that data. We can actually look at what has. We actually have household composition and everything else with our data. So we can actually investigate that one. That's a good point. Yeah. Okay. So my next talk is going to be a little more technical than this one. Just giving you more. That's all.